Hello everyone, welcome to our colloquium. Today we have Bridget Tenner and we are very excited to have her come and give us a talk. She's a professor in DePaul University. She's had her AB and AM degrees from Howard University under Richard Stanley. And MIT, where he got a PhD in mathematics. Combinatorics is a field of study, specialty research, and she has applied her research in various interdisciplinary studies such as voting schemes, how you can deal with gerrymandering and all that, but today we are not going to hear about that. We'll invite her again later to give talk about that, but today we're going to learn about combinatorics and their patterns. So without further ado, let's welcome Bridget.
Thank you. So I traveled all the way here from Fullerton, and I want to talk to you about what I do. And so my work is in combinatorics, which I think of as puzzles and games, but I know is related to the work of some people here in CDM. So one of my best friends in college, he and I took all our classes together, and then we went on to study the same things, except he ended up with a PhD in computer science, and I ended up with one in math. And so certainly I'm a lot more mathy than what you probably think about normally, but hopefully you will find some things that are appealing to you. And I don't know the background of everybody who's like watching at home or sitting in the room. So I like to err on the side of being too slow than too fast. So if it's not quite the right speed, maybe it's a little on the slow side, and I hope that's okay with you. So I want to talk about my style of combinatorics, and there are many different flavors of combinatorics. People do algebraic combinatorics, topological combinatorics. I do both of those, but I also do something called enumerative combinatorics, which I will try to give you a little taste of today. And a lot of the theme of my work has to do with patterns of various kinds. So I'm going to try to suggest some of those to you in this time. Okay, so first I should really say what is combinatorics. And besides being the topic with the most syllables, there is more to it than that. And so it's really the study of discrete structures. And this can mean lots of different things, but sort of at a fundamental level, this is what we're thinking about. And here's where you should already be a little more excited than you thought you would be when you heard it was a math talk, because it's not continuous things, it's discrete things. And so I'm thinking more like integers than real numbers. And you should probably then be wondering, what are combinatorial problems? Okay, discrete structures, I'm not sure what to make of that, but what kind of stuff do you do? Well, at a very basic level, combinatorial problems involve counting and sorting. And that sounds really easy, and maybe like, how do you get a PhD in that? So let me give you some ideas. So on a very basic sense, what does counting mean, and how can it be hard? Well, you know, you can do sort of the level 1 version of this would be like thinking about decks of cards and various combinations, and how many ways are there to get various combinations, and so what's the probability of getting a full house in a game of poker, that kind of thing. And that really relies on a whole bunch of counting problems. If you're commuting, right, you can look at the map and you can say, oh, there are these two different trains, and the red and the purple, and I can connect at various points, and I can count routes. And this is another kind of counting problem you can look at. You can also then, on a computer science side, think of sort of a combinatorial problem of understanding an efficiency algorithm, or the efficiency of an algorithm, I should say. And so the point of this list is not to say I do all these things and they're all fabulous research problems, like that middle one we can all figure out pretty quickly, but rather that counting can have different forms like this. Similarly, sorting, well, maybe you have something like a bunch of people playing tennis, and they haven't played all their matches against each other. You don't have complete information, you have partial information. And how could we look at a full ranking based on that partial information? So this would be taking a partial ordering, or a poset, and taking a total ordering, or a linear extension of the poset, And those are very fancy sounding words. But this is one type of sorting problem. You could also look at organizing data in a system or a database according to some certain structures or requirements. You know, presumably also something like a landing priority situation and a holding pattern in airplanes and different needs and priorities would then also require some kind of sorting. So weighing various bits of information and in different parameters and deciding what takes priority over what else. So these are counting and sorting types of problems. And so now let me tell you the sorts of questions I think about. So I think math is pretty cool. So this is not meant ironically. Two questions I ask about cool math objects or properties or applications. There are really two things I wonder. One is, okay, how many of those things are there? And what do they mean? So if I run into something that's pretty cool and mathy feeling, I do want to count it, and then I also want to know, does it matter? Right? Are there further applications? Is there relevance to this outside of just my own interest? And these are the two questions I want to show you about today. Okay, so this brings us to the idea of a pattern. And patterns are central to a lot of the questions we ask, certainly in mathematics, probably in some aspects of computer science as well. And so we should understand what a pattern is. Well, I'm just cribbing this from the dictionary. So a pattern is a form or model proposed for imitation. You might also think of it as a repeated decorative design, so some sort of pattern of tiles, something like that. Okay, well, what does it mean mathematically? What are patterns? Where are patterns in combinatorics? So, in fact, patterns come up in combinatorics in many different ways. So here's a very small list, and we'll talk about all of these. So we find patterns in integer sequences. So in sequences of data, we find patterns. We can find patterns in tilings, so domino tilings or rhombic tilings. And we can find patterns in graphs as well, and other places too. And what do I think of as a pattern? Well, mathematically, I think of a pattern as being like a small instance of something that you find sitting inside of a larger example. Okay, so if I'm looking at a big tiling, some beautiful mosaic, a pattern in that tiling is like a small chunk that gets repeated or maybe affected and repeated in various places. So these are very rough ideas of patterns. So let's think about this a little bit. Integer sequence patterns. So are you familiar with the online encyclopedia of integer sequences? Because you should be. Oh, somebody just shook his head, which broke my heart, but also makes my day, because I get to tell you about it. And you have a computer in front of you. So if you go, which is fine, I'm not judging. If you go to oeis.org, it is one of the best research tools in the world. It's outstanding. Online encyclopedia of integer sequences, because it began as an encyclopedia of integer sequences and later went online. But it's an amazing tool whenever you run into any kind of sequence of data. So I'll let you explore that later. But I want to talk to you about integer sequence patterns. Okay, so I'm about to show you a sequence of data. And there is an increasing subsequence. Oh, I have a typo. There is an increasing subsequence of length 3. Okay. So these are integers. And if you explore this for a minute, you might chuckle. And you might find an increasing subsequence of length 3. And if you don't chuckle, then I'm a little sad about my audience's pop culture references. But you can Google this later as well. Oh, I got it. Oh, okay, he's in now. He didn't know the OEIS, but he's got the song, so we're good. All right, so there's an increasing subsequence of length 3, and there it is, I made it red. Okay, so that means when I read from left to right, I'm finding numbers that go up. and three of them. They don't have to be consecutive. There are rules you can make about different kinds of patterns where you might say, oh, my pattern has to be actually a factor. It has to be consecutive, or maybe it has to be not consecutive. They have to be far apart, or maybe I don't care. And so there are different flavors of pattern avoidance and pattern containment. But just on its most basic level, this is the sort of thing you're thinking about. We will come back to this idea of a pattern of integer sequences a little later. Let's think also about tiling patterns. So tiling problems are a big area in combinatorics and in statistical mechanics and in some other fields as well. And people talk a lot about domino tilings, which is tiling by dominoes, 2x1 rectangles. People talk about tiling by lozenges or rhombi and various other things. And they're really cool papers and problems out there and beautiful pictures. So I want to talk just very briefly about domino tilings, just to give you a sense of how you can find patterns here. And in domino tilings of a region, you can look for patterns that cover a 2x2 square. Okay, so there are only two ways to perfectly cover a 2x2 square. And that would be by two vertical dominoes or two horizontal dominoes. This is not deeply creative in this picture. But you could do something like this, and maybe they're weighted in a certain way that you actually need to count up how many little appearances of this you have. And so that would be another kind of pattern, and with a much more geometric feel to it, although, like I said, it ties into these other fields as well. Now this is a fun one, because I said we're going to talk about graph patterns, and I bet you all knew what graphs were, and they were nodes and edges. But that's not where I'm going to start, because there's actually a really important Cartesian, like y and x, graph pattern that we are all used to, and we haven't thought about it in a long time, but it was really important. So a curve represents a function if and only if its graph avoids a certain pattern. What is that? Can you show me with a hand? Yeah, that was a good one. How do you know if a curve is a function? What did you have to do with your arm? Do you remember? You had to pass something, right? Yeah? Yes. The vertical line test. Yeah, you had to pass this, which means a curve is a function if and only if it avoids this pattern. That's not the way we usually think about function definitions, but that's exactly what you're looking for. And this idea of you have property x if and only if you avoid pattern p is something that comes up a lot in mathematics, and I'm going to show you more about that, give you some more examples in a little bit. But the idea of pattern avoidance equaling some kind of phenomenon is pervasive. And so here's probably the first example you thought about as a mathematician back in the day. And it was phrased differently, but this is exactly what we had going on. OK, so this is the kind of graph you already wanted to hear about. So I'm going to call this a combinatorial graph, or graph theory graph, if that's your thing. And so there are lots of nice theorems about these graphs. For example, you would say a combinatorial graph is planar, meaning it can be drawn in the plane with no intersections that are not actually at vertices. So a combinatorial graph is planar if and only if, again, there's that equivalence. If and only if, no subgraph. If and only if it has no subgraph, that is a subdivision of either of these graphs. Right? So you have to avoid K5 and K33 to be planar. So this is a classical result. You heard about it back in the day, but it's again a pattern situation. Okay. I want to talk to you about permutations. So now that we've got this introduction to patterns, I want to tell you about where I run into them a lot, or one place where I run into them a lot. So a permutation of a set is an ordering of the elements of the set. Okay, pretty standard. And I can give examples about lining kids up against the wall for lunch and to go out to recess or something. And yes, that's a permutation, but We all much prefer integers to people sometimes. So we're going to think about permutations of integers. So for example, if my set is the integers 1, 2, 3, 4, 5, here's a permutation of them. So my first position I have 5, my second position I have 1. 3 is actually just sitting in place. He didn't move. My fourth position is 2, and my fifth position is 4. So everything got reordered and put in place. OK, so here's your first quiz. How many permutations are there of this set? Math quiz time. I hope you know the answer and are just quietly keeping it to yourself. But you can also shout it out. I like how you all answered 5 factorial. That you didn't even say 120. You were like, 5 factorial? Yes. That's exactly right. Because I have 5 letters, and I have 5 choices for the first position, and then 4 choices for what comes next, and then 3, and then 2, and then 1. 5 times 4 times 3 times 2 times 1 is indeed 5 factorial. So there are 120 permutations of this set. OK, so there's our first counting problem. Very exciting. We all get an A+ on that. And you can obviously extend this if there are 6 or 12 or 111 elements in the set. We know how to figure out how many permutations there are. Great. What if I take this in a slightly more detailed direction, though? Instead of just thinking about permutations and factorials, let me think about permutation patterns. So let P and W be 2 permutations. They might not be of the same sets. W might be a permutation of 1 through n, and P is a permutation of 1 through something less than or equal to n. So if a subsequence in W has the same relative order as the letters in P, then I say that W has a P pattern. So this is like the integer sequence example we put up earlier. So here is my permutation from the last slide. And this permutation has 2 1, 2, 3 patterns. So P here is 1, 2, 3. And if you look carefully at our permutation, you see it has 1, 3, 4. That's in the same relative order as P. It also has 1, 2, 4, which is in the same relative order as P. And this is reading from left to right. This is what I see. So I would say that W contains a 1, 2, 3 pattern. In fact, 2 of them. On the other hand, it has no 2, 3, 1 pattern. So if you look for a moment or two, hopefully you convince yourself that from reading from left to right, you will not find medium, big, small. And in that case, I will say W avoids the pattern 2, 3, 1. As a little aside, for the most part, when you're talking about permutation patterns, it's a yes or no question. There's some work where you actually care about how much yes, meaning how many patterns. But for the most part, we just say, does it contain P? Does it avoid P? Okay? So here we have an example of containment and another example of avoidance. So now this is my question time, right? I said when I find something cool, I want to think about 2 things. And I think that was pretty cool. So my first question is, how many are there? So the question would really mean, if I'm given a certain pattern, how many permutations of n letters contain that pattern or avoid that pattern? And in fact, what ends up being more interesting usually is avoidance. So here's what I'm going to wonder about. Let's let n be an integer. So Sn is going to be the set of permutations of 1 through n. So this is also the symmetric group, which is where the S is coming from. So these are all permutations of n letters. You know there are n factorial of them. Very good. OK, so here's a question. Let me start with a really small pattern P. Let's say P is the pattern 2, 1. How many permutations in Sn avoid 2, 1? Any guesses? How many avoid it?
Avoid it.
Avoid it. I think you can show me with your fingers on this one. Yeah, yeah.
Yeah. Well, yeah, I thought it has to be all increasing. Yeah, one.
That's exactly right. 1. Because you have to never have a big and then a small somewhere down the line. So this has to be entirely increasing. So we have exactly 1 permutation. This is, in fact, the identity permutation. So this is good and bad. This was good because it showed us that we could actually answer this question sometimes. And bad is not quite the right word. Let's say good and boring. Good because we could answer it, and boring because it was like so restrictive that we got 1. Okay. So you could certainly pursue this by taking any pattern P, and you can, think about how you would determine if it contains or avoids P, and you could write a nice little algorithm for that. But let me give you a more interesting example now. And we're going to carry this example on. So how many permutations in Sn avoid this pattern, 2, 3, 1? Well, I gave you an example of one a little while ago that did. So we know that in S5 there's at least 1 that avoids it. That's not a very helpful piece of information, though. And so what you do as a combinatorialist, as a mathematician, perhaps as a computer scientist, is you realize you can't solve it in your head immediately, like you could with the first question. So you start writing out some examples, and you collect some data, and you make a list of data. So there's 1 permutation of 1 letter, there are 2 permutations of 2 letters. There are 6 permutations of 3 letters, but only 5 of them avoid this. There are 24 permutations of 4 letters, but only 14 of them avoid this. There are 42 permutations in S5 that avoid this. There are 132 in S6 that avoid this. And so you work out through S6, and you give up doing it by hand, certainly. You go to the OAIS, and you enter this information, because you say, hey, I've got this nice sequence of data. Does it mean anything? Do people already know this data? And they do. This sequence is a sequence of numbers called the Catalan Numbers, which are beloved to combinatorialists. And we will come back to them in a little bit. But these are so, they're sort of ubiquitous in combinatorics. My advisor recently wrote a book about Catalan numbers because there were so many things about them. There's a nice closed formula for them. They have many applications. But they also seem to be counting this problem about pattern avoidance. So because they are so important in combinatorics, that tells us that, hey, maybe there's something really interesting going on just in this little question, because it seems to be tied up to this enormously fabulous answer. So let's explore that. Because I have the second question. Remember, my first question was, how many are there? And if we just answered that, then I've got to move on. And then my second question then is, what does this mean? What are the 132 permutations in S6 that avoid 2, 3, 1? What do they mean? What do they have in common? What do they avoid? What's going on here? Okay, so we're going to explore this particular problem for a little bit. What does it mean to avoid this pattern? We don't know. So first we figure out what our question means, and our question means, is there any property that holds for permutations avoiding 2, 3, 1 and fails to hold when you contain 2, 3, 1? So is avoidance of 2, 3, 1 equivalent to something else that's going on? So maybe we start to list some permutations that contain it or avoid it. So here are some permutations that avoid 2, 3, 1. Here are some that contain 2, 3, 1. Not much to see there, right? I just gave you some random list of permutations. Hard to see a theme for these. So now I'm in the right place. Took a little detour on the red line, got down here. Okay, so this might be very familiar territory to you, but as a reminder, I'm going to put up some details. And also because maybe I don't use the state-of-the-art terminology, I'll tell you the words I'm using as I go. Okay, so stack. A stack is a data structure in which items can be added or pushed and removed or popped via last in, first out order. So I think of a stack as a stack of books or pancakes. And there we go. We push by adding a book to the top, and we pop it off by removing the topmost book. So this is the data structure we're going to think about. And I'm going to use a stack for a little maneuver. I'm going to say that a sequence is stack sortable if I can put it into the correct order, increasing order, by using a stack when I need to use a stack. I'm only allowed to use one stack. There are versions of this problem where you look at two stack sortable and so on. So what do? Well, here's my procedure. I'm going to start with an empty stack and an empty output sequence. And I'm starting with some string that's not in order or might not be in order, and that string is my input. So I'm going to repeat until the input sequence and the stack are empty. And if the stack is empty to begin with, or if the first letter of my input sequence is smaller than what's on top of the stack, then I take my first letter and I push it onto the stack. I'll give you a demonstration in a minute. On the other hand, if the input sequence is empty, or if my stack top letter is is less than what's coming out of my input sequence, then I start by popping the stack. So let me demonstrate. Okay, here's a sequence of data, 4, 1, 3, 2. I want to turn it into 1, 2, 3, 4. But I have to work from left to right. And so, for example, I see the 4 and I think, hey, I'm not ready for the 4 yet. So I put the 4 on hold by putting it on the stack. There it goes. Now I look at the 1. Well, I do want the 1. So I'm going to leave the 4 on the stack for a little while. I'm going to put the 1 on the stack, and then I'm going to pop it off. The 1 just kind of jumps across. Well, I wasn't ready for the 3, so I put it on the stack, but I want to leave it there. So now I see the 2, and then I pop that off, and I pop the 3 off, and I pop the 4 off. Ta-da! So our 4, 1, 3, 2 has gone into the correct order. Okay, so this is called stack sorting. At least to combinatorialists it is. And you might wonder what the connection is. Well, we can talk about stack sortable permutations. So I just showed you a permutation that I could sort using a stack, which is not a proof that every permutation can be sorted using a stack. As we all know, one example is not quite enough. You need 2. No. So let's give a definition here. Well, stack sortable permutations are permutations that can be sorted by stacks. And Don Knuth showed that a permutation is stack sortable if and only if it avoids the pattern 2, 3, 1. So that gives meaning to this class of objects I wanted. The permutations we were counting, those 132 permutations out of the 720 permutations in S6, those are exactly the 132 permutations that can be sorted by a stack. Now, I'm not going to walk through the proof except to show you what happens to 2, 3, 1 itself. So let's see why that's a problem. What happens to 2, 3, 1 when we try to stack sort it? What is the issue with this middle big small that breaks it? Okay, so I start here. I try to move the 2, but I don't want to move it all the way across because I really need a 1. Except with that 3 coming up next, I don't want to put 3 on top of the 2, so I try to pop the 2 off, I guess. And then I put the 3 on the stack. and then the 1, but now I'm stuck. Like there was no good way to be doing this. I can't get the 1 into the right place unless I screw up the 3. So the point here is that pattern avoidance can mean something. We've seen one example of that, but there are in fact many examples of a situation where you have avoiding this group of patterns, and it might be one pattern like 2, 3, 1, but it might be 6 patterns, might be 106 patterns. Avoiding those 106 patterns is equivalent to having a certain property that people care about. And that is a really interesting situation. So this is kind of extending the information we started with. So if you think back to the beginning of the talk when I talked about what patterns were, and first I gave you the 8675309 example, integer sequence. And I said this has an increasing sequence of length 3, and we found it, but that was not very interesting. We found the numbers 6, 7, and 9, and who really cared about that? But then we started talking about things like functions, and we did this, and we saw that avoiding these 2 dots on top of each other meant something about the curve. And then we looked at the combinatorial graph situation with planarity, avoiding 2 subgraphs, and that also meant something. And what we're seeing here is that permutation pattern avoidance can also mean something. So it's not just that we idly enjoy counting things that avoid a pattern in it. There's some deep meaning to some of these examples. Not all of them, perhaps, right? So I can tell you that there's at least 50 groups of patterns whose avoidance is characterizing some kind of phenomenon. And I have a database of them, like you can explore them, and it's really cool. But there's a lot that we could still figure out, a lot of things we don't know. So pattern avoidance can mean something. It can characterize a property, as you just saw. It can characterize stack sortability. In fact, it can characterize many other properties too. Some of those can involve highly abstract mathematics. Some of them are very easy to understand, like stack sortability. So there's a big range, like I said, dozens of things that can be characterized by pattern avoidance. So that's pretty cool. Now, let's take this back to counting just for a little bit longer. So I gave you this idea of the sequence of numbers that I said were the Catalan numbers. And let's try to understand this a little more. So remember that this Sn represents the group of permutations of 1 through n. So we saw a problem about how many permutations avoid 2, 1, and that was 1. And then we saw a problem about how many permutations avoid 2, 3, 1, and that was the Catalan numbers. And so you see that the different answers are possible, right? That's not a very helpful statement, but it's true. And if you do a little experimenting, you're actually going to find that sometimes 2 different patterns, they don't define the same set of permutations, avoiding them, but they might define equinumerous sets of permutations avoiding them. So if I have 2 patterns, P and Q, and the number of permutations in Sn that avoid P is equal to the number of permutations in Sn that avoid Q, just the number of them, not the ones themselves. They might be different sets. But if the 2 numbers are equal for all n, then I'm going to say that P and Q have some kind of equivalence. We will call it Wilf equivalence, named for Herb Wilf. So there is some kind of relation between them, perhaps. And the idea here, when we're wondering about Wilf equivalence, is when is it equally easy or hard, I suppose, to avoid P as it is to avoid Q? When are they kind of equivalently tricky to avoid as a pattern? Okay. First of all, this is interesting. We always want to check if that's true. There are some permutations that we will see in a moment that are Wilf equivalent, but not everything is Wilf equivalent. So, you know, we saw these 2 examples earlier, and one was 2, 1, and one was 2, 3, 1. Now, maybe I shouldn't be surprised that they are not Wilf equivalent, because 2-1 is a permutation of 2 letters, and 2-3-1 is a permutation of 3 letters. And so maybe those behave really differently, we don't know. But here are 2 permutations in S4, or 2 patterns of 4 letters, that are not equally hard to avoid. They behave really differently when you start counting. Okay. So I want to spend some time thinking about Wilf equivalence in S3. In other words, there are 6 patterns in S3, 6 patterns of 3 letters. And I want to figure out which of them are equally easy to contain. Can I group them up in some way? Well, we can be pretty clever and simplify this problem right away. For example, the patterns 1, 2, 3 and 3, 2, 1 are Wilf equivalent. It's equally easy to avoid 1, 2, 3 as it is to avoid 3, 2, 1. Why is that? Let's say I have a permutation that avoids 1, 2, 3. So I write it out. Well, if I just turn it around, then the result avoids 3, 2, 1. If I don't have small, medium, big, then I won't have big, medium, small. This is because 1, 2, 3 and 3, 2, 1 are reversals of each other. So here's an easy bijection that these two patterns are Wilf equivalent. For example, 3, 1, 5, 2, 4. Oh, that's a bad example. I'm sorry. That has a 1, 2, 3. You know what, though? It doesn't have a 3, 2, 1. So let's pretend I flip these. Shh, nobody will know. This avoids 3, 2, 1. And so if I turn it around, this avoids 1, 2, 3. Okay? I can do the same trick with 2 other pairs of patterns. I can just turn them around. 1, 3, 2 and 2, 3, 1 are Wilf equivalent. So are 2, 1, 3 and 3, 1, 2. This is great news. So we're seeing this question is pretty interesting in S3. I had 6 permutations, 6 patterns. I might have ended up with 6 different Wilf equivalence classes. But now it seems like I actually have at most 3. There's another trick I can do. I can complement. If you look at 1, 3, 2 and 3, 1, 2 for a moment, you'll see that they are, in a sense, complements of each other. If you were to add them component-wise, you'd get 4, 4, 4. So if I have a permutation that avoids 1, 3, 2, and if I take that and I make its complement, which means I replace each number by n plus 1 minus, excuse me, I think I'm going to sneeze. Okay. I take each number and I replace it by n plus 1 minus the number. Then I avoid the complement pattern 3, 1, 2. Let me demonstrate with an example that is hopefully correct. Yes. So here is a permutation that avoids 1, 3, 2. Here's its complement. You can check coordinate-wise, everything adds up to 6. And so this avoids 3, 1, 2. Okay. So this simplifies our Wilf equivalence classes a little bit more. Here's what we know so far. I started off with 3 groups, sorry. I had this pair, and this pair. But I just connected these 2 pairs. So there are at most 2 Wilf equivalence classes in S3. And then there was a very cool result. So this is by Simeon and Schmidt in the early 80s. And this result really kick-started the study of patterns, of permutation patterns, I should say. And what they showed was that these two patterns, 1, 3, 2, and 1, 2, 3, are Wilf equivalent. And once you know that, you actually discover that all the patterns in S3 are Wilf equivalent. All 6 of these are equally easy to avoid, or hard to avoid. Very briefly, let me show how they did this. They gave a really neat bijection. Start with a permutation that avoids 1, 3, 2. Fix the left to right minima. So as you read from left to right, every time you see a new smallest number, mark it, leave it in place, and take all the remaining numbers that are not left to right minima and rewrite them in decreasing order, which is a crazy thing to do. And once you do that, you avoid 1, 2, 3. So here is an example. Yes, this is an example. Good. So this avoids 1, 3, 2. As you read from left to right, the minima are 4, then 2, then 1. So I glue those in place. And then I'm going to take 5, 3, 6 and rewrite them as 6, 5, 3. I'm going to put them into decreasing order. And that result, by construction, avoids 1, 2, 3. This maneuver is invertible, right? So this is a bijection. And by doing this, they can say, OK, anything that avoids 1, 3, 2 corresponds to something else that avoids 1, 2, 3, and vice versa. And so now I know these are Wilf equivalent. So this is pretty spectacular. All patterns in S3 are equally easy, hard to avoid. So then you might get really excited. And you say, oh, OK, well, let me think backwards for a second. There's only one pattern in S1, so that's boring. In S2, there are 2 patterns, 1, 2, and 2, 1. You guys already answered the 2, 1 question. You said there's one permutation that avoids it. Similarly, there's one permutation that avoids 1, 2. OK, so the 2 patterns in S2 are Wilf equivalent. The 6 patterns in S3 are Wilf equivalent. So maybe everything, all patterns of a given size are Wilf equivalent. But we know that's not true, because I already gave you an example earlier of 2 patterns in S4 that are not Wilf equivalent. So in a certain sense, S1 and S2 and S3 are kind of too small to run into trouble like that. But as soon as you get into S4, it gets much more interesting. You get more than one equivalence class. And in fact, the equivalence classes are not all the same size. So there's some really interesting stuff going on. You can still do things like reversal and complement, but that only gets you so far, and then you have to use different techniques. And a lot of this is open in many senses. So this is very cool. So they're equally easy or hard to avoid, and then we say, OK, but how easy or hard? Because we like to count things. Everything comes back to that. And with various bits of work, we find that the number of permutations in Sn that avoid 2, 3, 1, or really that avoid any one of those 6 patterns, is this number. So this is very similar to the central binomial coefficient. And these are the Catalan numbers. As I said, fabulously important. Up there with Fibonacci, maybe above Fibonacci in our hearts at least. Oh, sorry about the microphone. So these are the Catalan numbers, and they enumerate more than 200 different classes of objects. So I've just told you 6 classes of objects they enumerate. Right? They enumerate the permutations that avoid 1, 2, 3, or 1, 3, 2, or 2, 3, 1, or 2, blah, blah, blah. But they also have to do with triangulations of polygons. They have to do with dict paths of various lengths, et cetera, et cetera, et cetera. Very cool list of things that they enumerate. And those objects then can be related to things like combinatorics, computer science, topology, number theory analysis, probability, geometry, et cetera, et cetera, et cetera, et cetera. And so these numbers are kind of everywhere, including in permutation patterns. So thank you very much for listening.
Any questions from the speaker?
Marcus.
Is Wilf equivalence a finite property? Is it decidable? Do you know how far you need to look in and to decide?
Ah, okay. So if I were to gather data somehow through like S10 and I thought things were Wilf equivalent, would that be a guarantee?
That's right.
So I don't know the answer for sure. My guess is no, but only because really like annoying things can happen when you are allowed more freedom. So I don't know for sure. I do know that we are often frustrated by just the computability of certain things. Like it's hard to gather data beyond S10, certainly. So yes, I'm not sure.
Permutation you explain here, here as you explain, the elements are sorted by algorithms which consist the internal storage is limited to a single data structure.
Yep.
I'm just wondering whether there are some sorting algorithms which you use some multi-step data structures.
Yeah, so the question had to do with the stack sortable example, or phenomenon really. And in that setup, I'm allowed one stack, which was great, but you could see that 2 stacks might be better. Why not? Let's collect some stacks. Sounds like my office at home, just stacks of things everywhere. And you end up with interesting and different results. So for example, having 2 stacks does change things. You are able to sort more things. And I'm not going to remember the exact answer off the top of my head, but if I remember correctly, the 2-stack problem leads to a slightly, so that also can be characterized by pattern avoidance, but the flavor of pattern avoidance is a little different. Because there's some more subtle things going on, that's when we ended up with, I believe, barred patterns, which are kind of patterns with a condition attached to them. And some work, I think, has been done with 3 stacks and so on, and there's some really interesting kind of variations of this result that come out of it. Mm-hmm.
Just before you asked the question, I was going to say, what kinds of generalizations are there to stack sortable? So having more stacks is one. Wondering if there are any other kinds of mechanisms to use other than stacks for generalizing this.
Yes, I think there has been work with some other kind of structure, storage structure in the middle, but I didn't do it, so I don't want to claim anything too careful about it. And yes, so my vague memory is that yes, some work has been done, but you could definitely do more things too, right? I think if work was not done further, it was more because of an unfamiliarity with other structures that were available and not because it was not fruitful.
Quick question.
Mm-hmm.
So what if we change that first in, last out stack to first in, first out stack?
Yeah. Right, so,
Yeah,
yeah, to a queue. So you could put things on it, well, but you have to allow a few other things too. You have to allow yourself to skip the queue. You have to allow budging. Right? Right? Because as it's set up, everything has to go through the stack and then either hop right off or stay. And if everything has to go through the queue, then we're just like moving our input to the queue and then to the output. But yeah, you should allow budging. Jump the line. There's so many applications. I don't know the answer. That doesn't mean it hasn't been done. I just don't know off the top of my head. But maybe it hasn't.
Priority queue.
Okay. It's like the airport.
Do you know how many times you do have to do stack sorting to sort for?
Yeah, so that's another thing that's been looked at, and I don't remember off the top of my head. Yeah. But what does it mean to do stack sorting to something that...
Just repeat and repeat until it's sorted.
What's your intermediate answer, though? Like with 2, 3, 1, what's... You have to define it carefully.
Shuffling, is that?
Does it sort at the end? Like if you keep repeating it, does it within n, if you repeat it n times, are you guaranteed a
Yeah.
sorted?
I think you have to...
Like,
Yeah.
It eliminates, certainly it eliminates a pattern, but it doesn't eliminate them all.
Well, but like with 2, 3, 1,
Right.
that doesn't get sorted, but it's also not clear what gets output, because it kind of breaks, right? So if you define some allowable off-ramp to go back to the beginning, then maybe you can answer that problem. But at the moment, I'm stuck with something in the stack. Sorry, huh?
I have another question. So my area is a little different to your area. So one of the areas that is mentioned is this topology. So we're working in this robotics area. We have little modules, and they get together to make different entities. So I was wondering if there's like any relationship that could be applied to such a system.
What do you mean?
So we have like modules, identical modules. So it's like Lego.
Yeah.
So you can assemble it to different forms. So like essentially we're playing with the topology of the robot. Are there like any related research involving this research and robotics? It looks
Not
very
that
far away.
Yeah, not that I know of.
If you have constraints associated with these modules, you could potentially formula this as a constraint satisfaction problem. You want to avoid this specific pattern. That's a constraint that you want to avoid.
Right, so in a very big level, you could think of the modules as satisfying pattern requirements. But in terms of the specific setup for patterns, I'm not sure, but maybe. Yes?
I was thinking, is it possible that you could have multiple patterns that are equivalent to a single pattern? And I'm not even sure that that could actually even happen. If you have a set of patterns you got, is it possible it's equivalent to a smaller set?
So when you talk about multiple patterns, P and Q, you have to avoid both of them. So you have to avoid P and avoid Q. That will not be equivalent to avoiding W. But there are some, I was sort of alluding to it before with the question about 2 stacks. There are some other flavors of pattern avoidance, things called barred patterns, vincular patterns, mesh patterns, marked mesh patterns, and so on. And some of those, what sound like very different setups for patterns, end up being equivalent to something in the classical pattern sense. So in the grand picture of permutation patterns and all that that entails, there is some overlap and duplication.
Any more questions?
Oh, yep.
So I don't know if this is, when you talk about tiling patterns, what I'm familiar with patterns is kind of repeated patterns where you use group theory to kind of describe what they look like. But is that what you're talking about?
No.
Or you're talking about something else?
Well, when you say the word repeated, I think the word tessellation.
Right.
And that's not what I mean.
Okay.
That's stronger than what I mean. So, but I mean, again, like I was saying to Marcus with the flavors of pattern avoidance, you can characterize a pattern problem in that way as well. So all of these fit under the umbrella of pattern. Typically, like with the list of things I gave, it would be something like, if you have this pattern anywhere one time, then something happens, right? Like if you have K5, you're not planar. Tessellation would be a different category of things.
I have one last question, sorry.
Yeah.
We have like 2 minutes. It's again related to this topology. To go from one topology to the other, you need to follow a set of intermediate shapes, if you will. Right?
Mhm.
For example, let's imagine a robot with 4 legs and a body, each made out of the same unit, identical units, and you want to make a snake-like serial system. So then you have to come up with some sort of a sequence of operations until you get to that shape, final shape. I'm not sure. I'm not sure, and I don't think we don't know the answer to. But can this be used to find out the intermediate sequences that can get stuck? Because you need to follow a certain order, right? If you follow a different order, you might get stuck, and then you have to go back and start again.
I mean, I wonder if you want to be phrasing it as, again, a problem about restrictions, and if you can encode the different positions of the different modules and how they are connected, and if you can encode the forbidden patterns between them, you can't have your elbow over here or something. That might be one way to do it. Alternatively, maybe what you're talking about ends up not encoding a forbidden state, but encoding a forbidden step between 2 states.
It's like this step, right?
Yeah.
If you go to that one, then you cannot
Right.
go ahead.
Right, you stall there. So possibly, but again, it's going to depend on how you write it down.
Yes,
Yeah.
definitely, yes.
Yeah, yeah.
Definition.
But maybe.
Any questions? All right, then let's thank again our speaker for a wonderful talk.
Thank you. Thanks for having me.